In this video, we will use the program not for calculation of photonic crystals, but to calculate ordinary surface plasmons in Kretschmann geometry and long-range surface plasmons in symmetric geometry. In Kretschmann geometry, a thin metal film is deposited directly onto a prism. To get this geometry, we should to go to the second step, with any parameters, since in step 2 we will simply manually set the structure that we want. We reduce the number of layers and take a gold film with experimental values of N and K. Let's take a look at this structure. Here, we have a prism. This is a 47 nanometers film of gold and then air. At first we look at the angular dependence of reflection and transmission, and see the typical pattern of the Plasmon resonance curve. This is the angle of total internal reflection, and this is the dip of the Plasmon resonance, due to the excitation of surface plasmons. We see that the propagation length is very small, about 4.5 microns. The dispersion curve looks like this. We see that somewhere around here is the surface Plasmon frequency, that is, the Plasmon frequency of the electrons in gold divided by the root of 2. We also see that longer propagation length can be achieved within infrared range. Let's go to step 1, set the wavelength to 800 nanometers and look at the angular width of the resonance. Indeed, our plasmonic curve has become narrower, and the propagation length has increased from 4.5 to 20 microns. We can of course change gold for silver for better resonance. Silver is a good plasmonic metal and we see that the propagation length increase a little more, to 30 microns at 800 nanometers. We can look at the structure of the field inside the layers. We see that we have an asymmetric structure. This is the Kretschmann prism. This is a gold film, and this is an evanescent wave in the external environment. The situation can be dramatically improved by making the design symmetrical, with air on both sides of the film. That is, when we have a golden film suspended in the air. Then our Plasmon curve splits into two, and both a long-range branch and a short-range branch appear. You can also see it on the angular curve. This is the long-range branch and it is the short-range branch. As we can see, the propagation length has grown significantly. Moreover, if we start to decrease the film thickness, then the two curves will diverge even more, and the propagation length will increase even more in the correspondent, long-range, branch. We see that this structure has a propagation length of 417 micrometers. This is achieved due to the fact that the structure becomes symmetrical and now we have zero tangential field component inside the metal film. As a result, the attenuation in the metal film becomes smaller and the wave propagates over long distances. But, it is clear that it is technologically more difficult to implement such a structure. After all, this is a thin gold film suspended in the air. This is the reason why we used the geometry with photonic crystals. The main idea is that here we can use a photonic crystal as a substrate for a metal film in the Kretschmann geometry and achieve the same propagation length as in a symmetrical structure. That's all.